Hello again, statisticians, here with an introduction to the normal curve. So the normal curve is more broadly known as a density curve. And if you think about the idea of, for instance, a histogram, um, and it has all these individual bars, if you were to replace that histogram with sort of a tracing over the top of it, which you see even a little bit in calculus to a degree, and make those smaller and smaller rectangles and so forth, where we can make this one a little taller and that one a little taller yet, and so forth. Eventually, we transition to what's called a density curve, where it's not in individual bins, but is really more of just a total area under a line that could be straight or it could be curved. So it could look like that, or it could look like this. These are both density curves. Okay, this is a density curve. The only thing that holds true for all density curves are these 3 points right here, which is that the area is always 1. And the reason the area is always 1 is because it represents the idea that 100% of the area is under each one of these curves. Okay, it always has to be above the horizontal axis because you can't go into a negative probability. Okay, 0% is the lowest. You aren't going to have a spot where there's a negative situation. And what we're interested in is the patterns of these. And like I said, when I started this lesson, this one's going to be mainly about the normal curve here. But density curves are a bigger, broader idea. And if you think about a situation where this is the option, that means that the probability of getting anywhere on the spectrum is exactly the same. Um, versus something like this, where it's more likely that you'll be around the mean and less likely that you'll be further away from the mean. So as I mentioned, here are some different types of density curves. This is what's called uniform. This would be skewed to the left right here. This would be skewed to the right. We talked about how skewed to the right is a lot of things that have to do with money. Home values, incomes, things like that are skewed to the right. Here's just an unusual one. But again, the area under all of these is exactly 1, and notice that none of them go below the axis. I referenced this a little bit last unit, but in skewed curves, it's important to note that naturally the highest point of the skewed curve is the mode. That's the most likely individual occurrence, whether that's an individual height or an individual income or whatever it may be. And with the skew, the median gets pulled a little bit to the skew. Important to note that the median is where it's 50-50 on each side. Okay, so it's the 50th percentile. The mean is going to get dragged out by that skew. So those extreme values on either end there will pull that mean further out. And that has to do with the mean being non-resistant and the median being resistant. So that's the difference there between the two. And again, that's something you'll see in skew distributions. Now, the median I noted is the 50-50 point. The mean is the balance point. So that's kind of like if you balance a basketball on your finger. If you were to try and balance the curve on your finger, that's where the mean would be, and so that it would actually stay on your finger. Mean and median are the same when it's symmetric. So if you do have a perfect bell curve, which that drawing is not, but if you did, the mean and the median would both be dead center on that. Q1 is the area where 25% of the area is to the left. Just like in a set of numbers, it's the area where 25% of the values are there or less. Okay, this is like you would see on your ACT results or some test results, but what percentile you were at. If you finish at the 25th percentile, that means out of a random group of 100 students, you're going to be tied or better than 25%. If you're at the 75th percentile, you'd be tied or better than 75%. Or if you're at the 75th percentile for height, that means you are the same height or taller than 75% of people in that population. Finally, here is just a little breakdown of what's called the standard normal curve, or in this case, the normal curve, or I should say, in this case, the standard normal curve because of the scale. We're used to seeing that with the standard normal curve. Okay, but this is a normal curve. If it's on this -3 to 3, that typically means we're working with the standard normal curve. That just means these are what are called z-scores, which we'll get into next lesson. But what happens with the normal curve, and if you think in the real world, things like ACT and SAT, Heights of fully grown individuals tend to follow the normal curve. IQs follow the normal curve. So what happens is the 0 represents being 0 standard deviations from the mean. Okay, so that is the mean. So this would be the mean right here, which we would denote as mu in a typical scenario. And then these values represent down here the number of standard deviations above or below, above or below the mean. Okay, and so what we're seeing here is if you look at this space here, the full blue space, that's about 68%, 68.26%. That means that about 68% of the values are within 1 standard deviation of the mean. So 68% of IQs are within 1 standard deviation of the mean IQ, and that tends to be at about 100 for the mean, with a standard deviation of about 15. So 1 standard deviation above is 115, 1 standard deviation below is 85 for the general population. You know, if you change your population group, that could change with each one depending on the group that you're involved with. So 2 standard deviations above the mean would be 130, 2 standard deviations below would be 70. And as you can see here, if you add all of those up in the second number there, that's about 95% of the population is going to be within 2 standard deviations. It rounds, the exact is a little different, but it rounds to about 95%. So 68% means plus or minus 1 standard deviation. 95 is plus or minus 2 standard deviations. Again, this is from the middle. And finally, 99.7 is plus or minus 3 standard deviations. So almost everybody is within 3 standard deviations of the mean. And there's a very small percent that are just above that 3 standard deviation mark or just below. There's really no end to the scale here, but typically that last 0.13% is probably going to be in between the 3rd and 4th standard deviation, with the rare occasion that somebody gets beyond 4 standard deviations, which has happened in a scenario where you maybe take some of the best baseball hitters ever and compare them to the mean and standard deviation for that year, and they may have been over 4 standard deviations above the mean batting average. So that's just an example of that. So the 68, 95, 99, 7 is called the empirical rule, and that just references the general breakdown of a normal curve. And so you could get any question here. For instance, what percent of the population is between the mean and 1 standard deviation above? So that would just be referring to this area here. What percent of the population is between 1 and 2 standard deviations from the mean? So that would be this one and this one added up. So about 27% are between 1 and 2 standard deviations from the mean in either direction. But again, this is going to be the general makeup of anything that follows the normal distribution. We'll get into next lesson the idea of working off of the actual values versus what I had noted before were those z values, which is just based on how many standard deviations you are away rather than your actual values. We'll leave it at that for this one. If you have any questions, as always, please ask. Thank you for watching.